Hello and welcome you all. In this presentation, Introduction to Parallel Programming with OpenMP. Today we will embark on a journey into the exciting realm of harnessing the power of multiple processors to unlock unprecedented level of performance and efficiency. So these are the topics which we are going to cover today. The first we go through Introduction to Parallel Programming, in which we introduce the concept of parallel programming and discuss its benefit. We will also discuss the different type of parallel programming models and the challenges which are involved in parallel programming. Then we introduce to OpenMP. So when we introduce to OpenMP, what is that? It is a popular parallel programming API. We will discuss the different OpenMP construct and how they can be used to parallelize application. Then we go through the modes of program execution, that is how we can compile and run our OpenMP program. In this digital era, where the demand placed upon computing system continue to grow exponentially, the traditional sequential approach to programming can no longer keep pace. To overcome these challenges, parallel programming emerged as a beacon of hope, enabling us to break free from the limitation of sequential execution and unlock new technique of computational capability. But what exactly are parallel programming, you might ask? For this, we first know about traditional or serial programming in which task is divided into instruction and executed sequentially one by one on a single processor. Parallel programming involves dividing a computational task into smaller, more manageable parts that can be executed simultaneously on a multiple processor or computing resources. By distributing the workload across these parallel resources, we can exploit the power of parallelism and achieve remarkable speed up and performance gain. Let us consider a simple example to explain parallel programming. Imagine you have a large data set containing millions of records, and you need to perform some computational intensive operation on each record, such as data transformation, analysis, or filtering. In traditional sequential programming, you would process each record one by one, performing the necessary operation before moving on to the next record. This approach can be time consuming, especially when dealing with large data sets. Now let's apply parallel programming to solve this problem. Instead of processing the record sequentially, we divide the dataset into smaller chunks and distribute them among multiple processors or computing resources. Each processor works independently on its assigned chunks, performing the required operation simultaneously. By leveraging parallelism, we can significantly reduce the overall processing time. While one processor is working on a chunk, the other processor can concurrently process their respective chunk. This parallel execution harnesses the power of multiple processors and allow us to process the dataset in much shorter time. Now we will see what is the need of parallel programming. So in the world of computer science and software development, the need for parallel programming has become increasingly evident. As our technology landscape continues to evolve, the demand of handling complex tasks efficiently has grown. Parallel programming, simply put, involves breaking down a large problem into smaller and more manageable tasks that can be executed simultaneously. By leveraging the power of multiple processing unit or cores, parallel programming allows for the execution of these tasks concurrently, which lead to a multitude of benefits. One of the foremost advantages of parallel programming is improved performance. With the ability to distribute workload across multiple processors, tasks that would traditionally require significant time to complete can now be executed in parallel. It significantly reduces the overall processing time. This boost in performance enables application to handle resource-intensive operation swiftly and deliver faster result to end user. Moreover, parallel programming facilitates better resource utilization. By dividing the complex task among multiple core, each core can focus on a specific portion of the problem, which optimize the use of available processing power. This efficient allocation of resources help us to maximize the system performance and prevent any potential bottleneck that may arise when executing tasks sequentially. Scalability. Scalability is another crucial aspect which address the by the parallel programming. As data volume and computational requirement continue to grow, programming enables system to scale up by distributing the workload across additional processor or computing node. This scalability ensures that the system can handle large and more complex problems without sacrificing performance or efficiency. In addition to saving time, parallel programming can also save money. By harnessing the power of parallelism, organization can optimize their hardware utilization, which reduce the need of additional hardware investment. With parallel programming technique, existing resource can be fully utilized, resulting in cost saving and improved return on investment. So how to do parallel programming? Parallel programming involves breaking down a problem into smaller tasks that can be executed concurrently. There are two primary approaches to parallel programming: task parallelism and data parallelism. So these are the two primary things. Additionally, parallel tasks often require interaction, which can be achieved through shared memory or message passing. Let's go to the problem decomposition. Task parallelism. In task parallelism, the problem is divided into smaller tasks, and each task is assigned to have different processing unit or core. These tasks can be independent or have dependencies on each other. Data parallelism. In data parallelism, the problem is divided based on the data. Each process unit or core operate on a different subset of data. Simultaneously, this approach is suitable when the same operation need to be performed on multiple data elements. Then in the task interaction. So in the task interaction, the first one came is shared memory. Shared memory is a form of parallel programming where multiple tasks can access and modify shared data in memory. This approach requires synchronization mechanisms such as locks, semaphore, or atomic operation to ensure data consistency and avoid race condition. Then there came message passing. Message passing involves communication between tasks by explicitly sending and receiving messages. Each task operates independently and has its own private memory space. Message passing can be implemented using libraries or communication protocol like MPI, that is also called as message passing interface. Now we will see why parallel programming. So in the world of computing, parallel programming has emerged as a powerful solution for tackling complex computational problems. This approach utilizes multiple processor or computing unit to execute tasks concurrently, providing several key advantages in various domains. One of the areas where parallel programming has proven invaluable is in the weather prediction model. Weather forecasting involves analyzing vast amount of data and performing complex simulation to predict future weather pattern accurately. Parallel programming also plays a crucial role in climate modeling. Climate models simulate the Earth climate system and help scientists to understand the complex interaction between the atmosphere, ocean, land, and ice. Then the one more thing came is genetic sequencing. Another area that greatly benefits from parallel programming, it involves analyzing DNA sequence to understand genetic variation, diseases, and evolutionary relationship. The vast amount of genomic data generated in these studies demand efficient processing technique. Parallel programming also addresses the challenge which is posed by the large data size problem. As dataset continue to grow exponentially, traditional sequential process become impractical. By employing parallel programming techniques such as data parallelism, organization can process and analyze vast amount of data in parallel and accelerating tasks like data mining, machine learning, and big data analysis. So we can say that Parallel programming also finds application in various domains. Furthermore, parallel programming is well suited for hybrid problems that involve multiple computational approaches or algorithms. For instance, problem that combines simulation, optimization, data analysis can benefit from parallel programming by distributing the workload across different processing units and allow them to efficient integration of diverse techniques and reduce overall time solution. Finally, parallel programming is crucial for time-critical problems that require real-time and near real-time solution. Now we will see what are the general terminology which are used in parallel computing. So it is essential to understand some key terminology that describe different approaches to managing memory in parallel system. Two commonly encountered concepts in parallel computing are shared memory and distributed memory. Shared memory refers to a memory model where multiple processor or processing unit can access and modify the same physical memory space. In this model, each processor operates independently and can read from and write to shared memory location. Changes made by one processor are immediately visible to other processors which are accessing the same memory. This shared memory model simplifies communication between processors since they can exchange data simply by reading from and writing to shared memory location. However, it also requires careful synchronization mechanisms such as lock or semaphore to ensure proper coordination and prevent data inconsistencies when multiple processors access and modify shared data simultaneously. Shared memory architecture are commonly found in multi-core processor and shared memory parallel computer. On the other hand, distributed memory refer to memory model where each process unit or node has its own private memory space that is not directly accessible by other processing unit. In this model, processors communicate and exchange data through message passing. Each processor operates independently and executing its own code and managing its own memory. To share data between processors, explicit communication is required. Typically, it is accomplished by sending and receiving messages. The message passing mechanism allows processors to exchange data while maintaining their own separate memory space. Distributed memory architecture are commonly employed in cluster of computer or distributed system where each node has its own memory and communicate with other nodes through network. Example of message passing library which are used in distributed memory system are include MPI, that is message passing interface. So to understand the distinction between shared memory and distribution and distributed memory, it is crucial when designing and implementing parallel algorithm and system. The choice between shared memory and distributed memory depend on factors such as architecture of the parallel system, the communication requirement of the application, and the nature of problem which is being solved. Each memory model has its advantage and trade-off in terms of ease of programming, scalability, communication overhead, memory access latency. So these are some more terminology. Let's go one by one. Node. Node is a standalone computer in a box. It is usually comprised of multiple CPU, processor, core, memory, network interface. Nodes are networked together to comprise a supercomputer. Now CPU. It is a contemporary CPU which consists of one or more cores. Now see what is process. A process is an instance of a program that is being executed, processed. Thread. Thread is a segment of a process or it is called as a lightweight process that is managed by the scheduler independently. Now see this diagram. So let's understand a cluster in more detail. A cluster is a group of nodes that are connected together and work together to solve a common problem. A node typically refers to an individual computing unit within a parallel system. It can be a physical machine, a server, or a virtual instance, or in a distributed computing environment. Each node typically consists of one or more CPUs or processor along with associated memory and other resources. A socket is in the physical socket or the motherboard where a processor is installed. A socket can hold one or more processor depending on the type of socket. A CPU or a central processing unit is the core component of a computer or node which is responsible for executing instruction and performing calculation. CPU are the primary workhorse of parallel computing, and the number of CPUs within a system determine the level of parallelism that can be achieved. A process in the context of parallel computing refers to an instance of an executing program. It represents a running program with its own memory space and resource. Processes are typically independent and isolated from each other, meaning that they do not directly share memory or resources. Let's say a thread. A thread, sometimes referred to as a process, it is a unit of execution within a process. Multiple threads can exist within a single process and they share some memory and resources. So parallel computing often involves coordinating multiple nodes, CPUs, processes, and threads to achieve efficient and scalable execution. Understanding the distinction between these terms is crucial for designing and implementing parallel algorithm and system with proper utilization of management of node. CPUs, processes, and threads are the key consideration in optimizing parallel application for performance, load balancing, and resource utilization. So before we start the programming, I want to know what kind of architecture we are using and how many core and socket we have inside our system. So we have one command. If you type lscpu or you type cat slash prop slash cpu information, you can see the following information on the terminal. So this is the information of our Paramsiva system, where you are seeing there is a 64-bit architecture having a number of core is 48. That is CPUs here you're seeing the 48. Now, what if I want to the information about my running process? Then for that, I can use a command called top-u and your username. If you type this command, you can check what you are running basically what are the commands you are running and how much CPU memory is being utilized by this command. Now, what is OpenMP? So OpenMP stands for Open Multiprocessing, and it provides an application programming interface that enables shared memory multiprocessing programming in languages like C++ and C and Fortran. OpenMP is designed to simplify parallel programming by using a directive-based approach. It allows developers to parallelize their code without extensive modification. Essentially, OpenMP helps us make the most of multi-core processor by dividing the workload among threads and enabling parallel execution. OpenMP comprises of three primary API components. The first one is compiler directives. It is a special annotation which are inserted into the source code to guide the compiler in parallelizing the code. The second one is runtime library routine. It is a set of functions that manage the creation, synchronization, and termination of threads. The third one is environment variable. Configuration setting that control the behavior of OpenMP program, such as number of threads to use. So this is covered by environment variable. OpenMP is designed to achieve portability across different platform and architecture. The API is specified for C, C++, and Fortran, making it accessible to a wide range of programming languages. It has been implemented for most major platforms, including Linux and Windows systems, which enable developers to utilize OpenMP on their preferred operating system. OpenMP is a standardization API that is jointly defined and endorsed by major compute hardware and software vendors. it has emerged as a fact that is standard for shared memory parallel programming. It is expected to become an ANSI standard in the future short version. So OpenMP is called as Open Multiprocessing. Open specification for multiprocessing achieved through collaboration work between interested parties from the hardware and software industry, government, and academia. Now see why OpenMP. So should we use OpenMP? Well, OpenMP offers several advantages. Firstly, it simplifies parallel programming by using directives. We can easily identify section of code that can be executed in parallel and specify this using directives. Secondly, OpenMP is portable across different platforms and architecture. It provides a standardized approach to parallel programming that work across various systems. Thirdly, OpenMP support incremental parallelism, meaning that we can gradually add parallels to our code without rewriting it from scratch. Some other features are like specify the parallelism, specify whether the variable in the parallel section are private or shared, specify how if the threads are synchronized, specify how to parallelize rules, and specify how the work is divided between threads. Now we will see the OpenMP development history. So OpenMP was initially developed in the later 1990s as a collaborative effort between several leading computer hardware and software companies, including Silicon Graphics, IBM, and Cray Research. The first version of OpenMP, OpenMP 1.0, was released in October 1997. It provides a set of compiler directive, runtime library routine, and environment variable to enable parallel programming in Fortran and C++. OpenMP 1.0 introduced key concepts such as parallel reason, work sharing construct, and data scoping. To keep up with advancement in hardware and programming languages, the OpenMP and industry-driven organization continue to develop and release new versions of OpenMP standard. Each new version introduces enhancement and additional features to improve performance and facilitate better parallel programming. Let's take a look at some key milestones in the history of OpenMP. So OpenMP 2.0 is developed, released in May 1998. It introduced critical section, loop construct, and tasking support. Then OpenMP 2.5, which was released in November 2001. It added support for nested parallel and introduced the OpenMP parallel section construct. Then OpenMP 3.0, it is coming released in May 2008. It brought support for explicit tasking, that is SIMD, single instruction multiple data construct, and additional loop scheduling option. Then OpenMP 4.0, it is released in July 2013. It introduced support for accelerators such as GPUs and provide a new feature for task dependencies and thread affinity control. Then OpenMP 5.0. OpenMP 5.0 released in November 2018 and it added support for deep copy semantics, improved GPU offloading, and introduced error handling mechanism. Now let's take a closer look how OpenMP works. So OpenMP follows a fork join model. What does it mean? It means that the master thread initiate a team of parallel threads to execute a parallel region and then rejoin them. Parallel regions are defined using compiler directive, which allow the code within those regions to be executed in parallel. Threads share the same memory space, enabling them to work cooperatively. Data can be shared among threads or made private to each thread as needed. Now see the OpenMP stack. So the first is application layer. At the top of the software stack is the application layer. This layer represents the user application code which can be written in language such as C, C++, or Fortran. The application code contains sections that can be parallelized using OpenMP directives, compiler layer, and OpenMP runtime layer. So below the application layer, this layer lies. OpenMP directives embedded within the application code are recognized and interpreted by compiler. Here the compiler analyzes these directives and generate parallel executable code based on them. It also performs other traditional compilation tasks such as syntax checking and optimization. The OpenMP runtime layer play a crucial role in the software stack. It provides the necessary infrastructure and runtime support for executing parallelized code. The runtime layer manages the creation and synchronization of threads, dynamically schedule parallel work, and handle data sharing and synchronization between threads. It ensures that the parallel code execute correctly and efficiently. Then the layer came operating system layer. So below the OpenMP runtime layer, it lies the operating system layer. The operating system is responsible for managing system resources, including processor, memory, and input-output devices. It provides the necessary services and abstraction for efficient thread management and synchronization. The operating system interacts with the OpenMP runtime library to allocate resource and schedule threads for execution. Then came hardware layer. As the bottom of the software stack is hardware layer, which consists of physical component of computing system. This includes the processor, CPUs or GPUs, memory, caches, and other hardware resources. The hardware layer execute the parallelized code and perform the actual computation. Now we will see how to write a hello world program in OpenMP. So let's explore the basic syntax of OpenMP directives, which plays a crucial role in parallelizing code and utilize the power of multi-core processor. OpenMP directives are compiler instructions that guide and parallelize process. To use OpenMP directives in your code, you need to include the appropriate header file. In C and C++, you typically include the omp.h header file. This header file provides the necessary definition and function for working with OpenMP directives. Most OpenMP constructs follow a similar syntax. They begin with hash pragma OMP directive, followed by the specific construct and any associated clause. The directives are enclosed with the curly braces to denote the parallel region or block of code that need to be executed in parallel. Let us consider an example directive. Hash pragma OMP parallel num underscore threads 4. So when I write this, I have to do some work here. So there the parallel region will be executed. Let's walk through a simple Hello World program which is implemented with OpenMP, a parallel programming API. This program serves as an introductory example to demonstrate the basic use of OpenMP directive. In this program, we start by including the necessary header file stdio.h for input-output operation and omp.h for OpenMP function and directives. The main function is the entry point of our program. We include the parallel code block using the hash pragma OMP parallel directive. The directive informs the compiler to create a team of parallel threads to execute the code within the parallel region. Inside the parallel region, we use the OMP getThreadNum function to obtain the ID of each thread. This function returns a unique identifier for each thread within the parallel region. We then use printf to display the hello world message along with the thread ID. Each thread ID executes this code independently, resulting in multiple greeting being printed. So let's see how the program is executed. When a program is executed, the parallel region is created and multiple threads are spawned. Each thread executes the code within the parallel region independently, resulting in concurrent execution. The printf statement outputs the hello world message along with the thread ID. As the program executes, you will see multiple lines of greeting printf with each line showing the thread ID, like hello world thread 0, hello world thread 1, 2, and 3, similarly like this. Now we see how we compile and execute a program. So the compilation of an OpenMP program involves several steps to generate executable code that can take advantage of parallelism. To enable OpenMP support during compilation, you typically need to specify the appropriate compiler flag. For example, if you are using GCC, that is GNU compiler, you can use the -f OpenMP flag. And if you are using the Intel compiler, that is ICC, you can use the -q OpenMP flag. This flag informs the compiler to recognize and process OpenMP directives. To set the number of threads using the environment variable, we have to set the variable export omp num underscore thread is equal to 4. Or we can set it using the runtime routine in the program, that is omp set num threads, or in the bracket we write 4. If both are given, it will consider the runtime routine as priority. The default number of thread is the available number of code. Once the compilation process is successful, the executable program is ready for execution. The execution process involves the following steps. That is, run the executable, that is / your executable name. Here we can see that in the C compiler, if we write gcc-f openmp, it is a flag if you want to compile an OpenMP program. That is, and you have to write your file name hello world.c -o, then your executable name. So here hello will be your executable, then execute that executable /hello. Similarly, if you're doing with the Intel compiler, you write ICC-q OpenMP, then your program name hello world.c -o, your executable name that is hello, then simply write /hello. So output of the hello world program here with 4 threads will be like this hello world 3012. Similarly, it will be like that. Now we will see and execute one OpenMP program for matrix multiplication, in which you will able to see if we write a matrix multiplication program serially, and if we write it parallelly using OpenMP, what is the time difference. So in this today's presentation, we have learned about OpenMP, but we have covered a very basic OpenMP part. And OpenMP is a large topic which is mostly covered in 8 to 10 hours. So here we have get a brief information about OpenMP and its how to execute it. Thank you.